Good morning, or whenever you're listening to this or watching this. It may not be morning, maybe evening or some other time. This is Danielle Mueller, and I am going to do the chemical composition review for the material that will be on the online open book, open note exam that is due on not this Friday, but next Friday at 3:30. So that'll be online. You go through my Mac to do that. The test is timed. You have an hour and a half to take the test. So you only have a limited amount of time to take it, and you only get one attempt. So make sure that when you go in to take that, you're ready and have the time to go in and do that. It's 50 questions, multiple choice, true, false type questions. So it's just through my Mac. So instead of coming and taking it in class. So like I said, you can use your book and your notes. So that is nice. It'll be the only test we take in here. It'll be online. It'll be the only test we take in here that you can use your book and your notes. So enjoy when we get to do that. All right. So to start off, physiology is the kind of the how everything works. So anatomy was the study of all the structures, and then physiology is the study of the function. And so it's kind of the chemistry and the physics of living things. So that's why we kind of go over this chemical review portion, because for some of you, it may be a few years since you took chemistry, and if you don't use it every day, it kind of goes away. So I wanted to kind of review the basics. So we're not doing stoichiometry, we're not balancing equations, it's not the nitty-gritty of chemistry, it's some of the basic concepts that are really going to be part of our physiology, so the biological portion of this. So we will be using that. So we're going to look at all chemical substances are made up of matter, and that matter ultimately the smallest full subunit, like the smallest living component of life is a cell. In chemical substances, that smallest unit is the atom. There are subatomic particles that make up the atom that we're going to see, but when we're looking at that most basic unit of chemical structure, it's going to be the atom. So we're going to kind of talk about that. So a lot of times in physiology, I get the question, when are we going to move out of the cell? We will work outside of the cellular level in a bunch of different things, but when it comes down to it with the physiology, we're going to look at a lot of these, how things work at the cellular level. So we'll never truly fully leave that cellular level. So if you weren't a big fan of things at the cellular level in anatomy, sorry, physiology is, we talk about a lot of things like, how does a muscle contract at the cellular level? How does a nerve impulse travel at the cellular level? I mean, like I said, we will talk about outside of the cell as well for the physiology at times, but we never truly leave the cell behind. So that's kind of an important thing to remember. So everything in our universe is made of matter, and it can exist in different states. So we know those states hopefully from in the past: solid, liquid, gas. All matter occupies space, so it takes up space, and it has some sort of mass, depending on if you're here or at the moon. The weight can vary because of the gravity, but the mass would stay the same, how much space I physically take up. So I take up the same amount of space here as I do on the moon, but my weight would be less on the moon because there is less gravity pulling down on me on the moon. So I would have less weight there. So weight and mass are different. Mass is how much space I occupy, how much space I take up. Weight, like I said, will vary with the force of gravity. So a lot of times people would try to use them interchangeably, but technically in science they are, two separate things. So when we look at atoms are that basic subunit of the chemical matter. And when we look at that, we're going to see that an atom is made up of subatomic particles. So it's made up of protons, neutrons, and electrons. So when we look at this little diagram here, we can kind of see this kind of cluster right here where we have the blue circles with the plus, those are representing the protons. The kind of the black circles here represent the neutrons. There's no positive or negative on those because neutrons are neutral. And then the little green, and then in some cases red, those are going to be the electrons. They represent them in different colors because some of the electrons belong to different atoms, but we can kind of see here the protons and neutrons are found in this kind of central structure here, which is the nucleus, and then kind of floating around in these orbits, we have the electrons. And we're going to talk more about the electron shells, how many you can hold in a first, orbital, a second orbital, things like that, and how that affects how they can interact, when we look at ionic and covalent bonding. So we'll kind of look at a little bit of this as we kind of move on from there. But here we're seeing this right here is the nucleus of our carbon atom. And then these ones right here with the 1+ here, those are our hydrogen atoms. And so we have 1 carbon and 4 hydrogen atoms that are coming together to make methane, and they're using that doing covalent bonding where they're physically sharing electrons. And we'll kind of look at that more in a little bit. So this represents the same thing here. It's just instead of drawing all of that out, they're using kind of the chemical formulas there. You will have to know some atomic symbols, the chemical symbols for some of the elements. It's not a whole lot of them. You, by no means do you need to go home and take the periodic table and start memorizing all of the things like, on the periodic table. I do want you to be familiar with some that we use a lot. Hydrogen is H, that's easy. Sodium is Na. That one's a little bit, you're like, sodium, why do we have Na? The Latin name for sodium is natrium. And so that's where that Na comes from. It comes from its Latin names. So a lot of times on the periodic table, if the chemical symbol doesn't really match up with the name, a lot of times it means that symbol came from the roots of the Latin name of that basically that atom. So sodium is Na, potassium is K, another one that comes from the Latin name there. Chlorine is Cl, magnesium Mg, calcium is Ca. On here, they're, they don't show you carbon. Carbon would just be C. So there are some that we will, basically need to know that symbol because as we talk about like nerve conduction and things like that, or membrane potentials and things like that, sodium and potassium are heavily involved in that. So we need to realize that when I talk about Na+ and K+ and things like that, Cl-, that you guys understand what, when I put down that symbol, what what atom or ion, if it's charged, it's representing. So we can kind of see that. So here it shows you chemical symbols for the ions. If they have a plus or a minus next to it, that means that is no longer an atom, it's an ion. It has gained or lost electrons. So we're going to look at those a little bit later. I'm not trying to get too much ahead. Sometimes I, start explaining things and then 5 slides later, I'm like, oh, here it is again. So sorry about that. So when we look at this, hydrogen, oxygen, nitrogen, and carbon are the elements. Those are the symbols for the elements that make up the majority of our body. So 96.2% of our body is made up of hydrogen, carbon, nitrogen, and oxygen. So those 4 elements make up the majority of our body. Then we have other elements that are in trace amounts that are important. Like I said, you would have the potassium, the calcium, magnesium, manganese. There's all sorts of other things that we find in much smaller amounts, but this makes up the biggest amount. So a lot of times to remember those, people remember HONC, like HONC. Sorry, it's not a K, but that helps you remember the symbols for those. So just remember 96.2% carbon, oxygen, nitrogen, hydrogen. So those 4 atoms. So here they are: hydrogen, oxygen, nitrogen, carbon. So it's showing you the symbol plus the name there. When we look at an atom, like when we kind of looked before at that one that showed methane with the carbon and then the 4 hydrogens around that, we kind of saw that kind of what's called the planetary model with orbitals, where you have the nucleus in the center, and then you have the electrons kind of orbiting around that, kind of like how, you know, the center, like the sun is the center, and then all of the planets orbit around that. So it's similar like that. That's why they call it a planetary model. It's the easiest one to kind of visualize. Do atoms run around in these very specific tracks? No, in reality, they don't just like go around in a ring like that. They're kind of in a cloud-like structure, but that's a lot harder to represent, and it's a lot harder to think about when we're looking at that atomic structure. So a lot of times they draw in kind of this planetary model, where here we could see hydrogen has one proton, one electron, and the proton's in the nucleus here, and then they get one electron, you know, kind of inhabits this orbital right here. Like I said, does it truly run in like a little track around there? No, it kind of forms like a cloud where it's going to be moving in this general area here, but this is the best way to kind of represent it, so it's easy for you to work with and kind of think about when you're working with atoms. So the nucleus is kind of like in a cell. The nucleus is located in the center. It contains subatomic particles, and those subatomic particles are protons and neutrons. So you're going to find protons and neutrons in that nucleus. Here they're showing an atom of hydrogen. It just has one proton. In this case, it has no neutrons. If you had tritium and deuterium, then we would start putting in neutrons in there. But right here, we're just showing one proton in that nucleus there. When we look at protons, think like the P for positive. They are positively charged subatomic particles. They're found in the nucleus. They have an atomic mass unit of approximately 1 AMU, so 1 atomic mass unit. So we can kind of see that. The protons are made up of what's called a quark, which are represented by up, down, and color. That's kind of just a fun fact. You don't have to know that for the test. So if you're like, we didn't learn that in chemistry, like if you took an intro to chem, they may have never mentioned quarks, and that's okay. You don't have to remember that. Neutrons are also found in the nucleus. They are a subatomic particle. They have about the same mass as a proton, so that's 1 atomic mass unit. So if you have, let's see how good I can write on here. So 1, and I do AMU, which is atomic mass unit. So 1 AMU that's the mass of that proton. And then since neutrons are roughly the same size, they're also 1 atomic mass unit. Neutrons, think neutral. They are neutral. They do not have a positive or a negative charge. So protons and neutrons both reside in the nucleus. Protons are positively charged. Neutrons have no charge. They're neutral. And they both have approximately the same mass, which is 1 atomic mass unit. So here we can kind of see in our atom of carbon here, we have protons and neutrons in that central nucleus. And then our electrons are orbiting around the nucleus there. All right, so I don't know, discard those. One day I'll figure out how to get out of a pin function without getting out of the PowerPoint. Today's not that day. When we look at protons and neutrons have approximately the same atomic mass unit, and that's that 1 atomic mass unit. When we look at electrons are significantly smaller. They, when you compare the weight of an electron to the weight of a proton or a neutron, that weight is negligible. So a lot of times when we start looking up the atomic weights and atomic numbers, they don't factor in the electrons at all, because their weight is so small that it doesn't really add to it. So you can kind of see here they're much smaller than that proton. So atomic mass unit, 1 AMU, the mass of your proton or the mass of your neutron. So we have protons and neutrons are the same, 1 AMU, 1 atomic mass unit. Electrons, like I said, significantly smaller. So 1/2000th of the mass of a proton. So if you had, if you can imagine, like, if you're, the mass of your proton or neutron is, let's say that it occupied this much space. this little cube that I'm holding with my hands here. Then if we looked at the mass of an electron, it would be 1/2000th of this mass. So if you took this block and divided it into 2,000 little mini blocks, we would have, you know, this would be the mass of that one electron. Very, 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 very small. So it's negligible when we look at the mass of that electron compared to the proton or the neutron. So they don't add that in when they're doing you know, the atomic weight or atomic masses of atoms. So it's much, much smaller. The electrons are negatively charged. So the protons are positively charged, neutrons are neutral, electrons are going to be negatively charged. When you have an atom is going to have the same number of protons and electrons. So an atom is electrically neutral because the electrons and the protons always equal each other out. The electrons are not found in the nucleus. Protons and neutrons are in the nucleus in that center. The electrons are in those orbits or probability shells. Like I said, we always draw them as like this, where you see them kind of running around that track. Really, it's more like a cloud where they're at any given place in that cloud at any given time. But that's hard to work with when you are, you know, trying to do math or figure out like the shape of things if you were thinking about it as a cloud. So we kind of draw them in these nice little orbits here. So they're located in these orbits. So we have, you know, this first orbit, second orbit, depending on how many electrons you have, you might have a third, fourth, fifth, depending, you know, on how many electrons you have. So when we look at the atomic number is the number of protons. So if you were looking at a periodic table, let me switch over here. The atomic number is the number of protons. We're going to share. So here's your little periodic table. So if you're looking at periodic table here, we can see they show one right here where you can see atomic number is right here. So hydrogen, they give you the name, the chemical symbol, and then this right here, this number, that's your atomic number. That tells you how many protons you have. If you have an atom of something, that also is telling you the number of electrons, because we know that the protons and electrons are equal in an atom. If you have an ion, then the number of protons and electrons are not the same anymore, but we'll get to that in just a minute. So this is telling us our atomic number right here, so the number of protons. So if we looked at, for instance, carbon has an atomic number of 6, which tells us it has 6 protons. If we went to arsenic here, so arsenic has an atomic number of 33, so it has 33 protons. So, you know, if you're given that information, if you're given the atomic number, then you know how many protons it has. Or if I gave you a question that talked about how, you know, an atom has 7 protons, then you'd be, you know, and you had access to periodic table, then you could look up what 7, oh, 7 is nitrogen. So like I said, you don't have to memorize the whole periodic table, so please don't. I don't think you have to memorize the whole table. All right, let's go back here. All right, so the atomic number is the number of protons, and when you're talking about an atom, that tells us also the number of electrons. So if I told you the atomic number of carbon is 6, I could then ask you how many protons and electrons does it have. You could say, oh, it has 6 protons. It also has 6 electrons, because we're talking about an atom, because atoms have no overall charge. So the protons and electrons are always equal in an atom. When you're talking about an ion, that is not true. The mass number is, I don't know why my little thing here became P. The mass number is the number of protons plus the number of neutrons. So mass numbers, protons, and neutrons. So if you were given, for example, if there was something that said, you know, you have you know, mass. Oh, let's do this. Let's go. Oh no. I like just get the thing I want you to show. It's up a little bit. So it's probably quicker and easier if I write on here versus on. All right, so if we look at this way so we can actually read it. If you had a mass number of, let's say, 13 and an atomic number of 6. Oh, okay. There we go. That tells us, when we look at this, since we have atomic number, this tells us this is the number of protons. Sorry, I'm writing sideways now. So, and then our mass number is the number of protons plus neutrons. All right, so if the question asked if you were given the mass number and atomic number and it said how many protons are there, so if it said how many protons, we know the proton number is 6. What if it asked how many electrons we have? So if it asked us how many electrons we have in an atom, so if this is all based on an atom, we remember in an atom, the protons equals the electrons, so we know the number of electrons is also 6. If it asks us how many neutrons we have, given the mass number is the protons plus the neutrons, so that's a total of 13 when those two are combined, and we know that the number of protons is 6, we would take 13 minus 6, and that's going to give us 7 neutrons. So if you're given the mass number and the atomic number, you can figure out if the number of protons, the number of electrons, and the number of neutrons from just those two values. But remember, this is for an atom, so our protons and electrons are the same. If they were talking about ions, they would have to tell you the charge associated with that ion so that you could correctly determine the number of electrons. But this is for an atom, so we can kind of see that. So this is pretty much as hard as the math gets for this chemistry review. So hopefully that's not too terribly bad. All right, let me go back. Screen here, so that's our mass number. An isotope, if we're looking at an isotope is when you have 2 or more atomic variants that have the same atomic number but different atomic weights. So when we look at things, if you've heard of like carbon dating, like carbon 14, there's carbon 12, there's carbon 13, there's carbon 14. All of them are carbon because they all have the 6 protons in them, but they're considered isotopes because if you were looking at carbon 12 versus carbon 13 versus carbon 14, the number of neutrons varies. So they're basically, that atomic weight is going to be different because they have differing numbers of neutrons. They're still all carbon because they have the 6 protons, but when you vary the number of neutrons, then you get a different, atomic weight. So the protons and the electrons are still the same, but the neutrons are going to be different for each different isotope when we look at that. So here, this is showing you one example of that. So this is hydrogen. So most of the hydrogen that we encounter in our environment is hydrogen that has 1 proton, 1 electron, and no neutrons. You also have deuterium and tritium, which are isotopes. All of these are isotopes of hydrogen. So 1 proton, so that's why it's still considered hydrogen. one electron, but now it has one neutron. So when we look at the mass of this one here, the mass of this would be 1. When we look at the mass of this, you have a proton and a neutron, each with 1 AMU, so your mass would be 2. Tritium has 1 proton, 1 electron, so still considered hydrogen because of the 1 proton. But then when you look at the mass of that, you have basically your proton and neutrons being added together, so that has an atomic mass of 3, so it has more weight to it when we look at those. So they're all isotopes because they're all hydrogen, but the number of neutrons is going to vary. Like I said, you could do this with carbon or other, usually people have heard of like carbon-14 dating, so sometimes people have heard of that, so they may be familiar with that, but you can kind of see that. So here this is showing those isotopes: 1 proton, no neutrons, 1 electron. Here's deuterium, 1 proton, 1 neutron, 1 electron, and then tritium, 1 proton, 2 neutrons, 1 electrons. All of them are considered hydrogen, but they each have a different atomic mass because of the differing number of neutrons, but they're all still hydrogen. So when we look at the average atomic weight, that's equal to atomic mass, but it's kind of the average of all of the different isotopes and their abundance. It takes the abundance into factor, so it's not just saying 1 + 2 + 3 and then you get the atomic weight. It would say if 98% of hydrogens are coming from our isotope that has 1 proton and 0 neutrons, it's going to add more to that weighted average. So when we look at our periodic table, if you looked at the atomic weight, the average atomic weight of hydrogen, it's 1.008. And like I said, when you look at these, sometimes you can kind of tell which one of your isotopes is most prevalent, most in the highest abundance, because this number is really close to 1. So that means that most of our hydrogen we encounter are not going to be deuterium or tritium. It's going to be our just plain old hydrogen that has 1 proton, 1 electron, 0 neutrons. With that, I am not asking you to determine average atomic weight from like the weights of the isotopes and their abundance. That I won't ask you to do that. You just want to know that when you look at that periodic table, so we went back here. There's a faster way to do this. All right, oops, put this book back over here. So when we look back at this on here, when you look at right here, that was our atomic number of protons, our atomic symbol. And then down here, a lot of times they call this average atomic mass or average atomic weight here. This value here is the average of all of the different isotopes together. So that takes in, and that's why these have decimal values with them. So if you're looking at some of these other things, like if you look at carbon, it's 12.01, here silicone is 28.09, phosphorus is 30.97. That's taking all the different isotopes and with their abundances and giving that average atomic weight there. So if you remember back to chemistry when you had to do the, like stoichiometry, or if you were going to convert from grams to moles or something like that, you'd have to add up all your atomic weights there. So you had your average atomic weight, use that in that kind of mathematical formula. Like I said, you won't have to do all of that in here. So that wasn't your forte or you didn't love it. You don't have to do that. So don't stress out with that. Some of the isotopes are radioactive, so they're considered to be radioisotopes. They're typically heavier and considered to be unstable, so they will spontaneously decompose into more stable forms. When we look at things like tritium, that is a radioisotope of hydrogen. Carbon-14, that's a radioactive isotope of carbon. Of course, when you look at things like uranium and radium, things like that, those ones are you find high abundances of those, the radioisotopes, when you're looking at that. Like I said, tritium is a small amount of all of the isotopes of hydrogen, but if it naturally and spontaneously decomposes into more stable forms, that's considered a radioisotope. When you look at radioisotopes, the rate in which they decompose to become more stable forms is described as half-life. So the time it takes for that radioisotope to lose half of its mass, that's going to be its half-life. So some radioisotopes, their half-life is in minutes. Some radioisotopes, their half-life is thousands of years. So when you look at like carbon-14, half-life is over 5,000 years. When we look at that, if you look at things like if you've ever had some sort of testing where they had you, ingest a radioisotope, maybe you had like iodine. They may have had you take in a radioactive form of iodine, and the half-life of that may be like 14 minutes. I don't know what it is off the top of my head. I'd have to look it up, but it would be a short half-life because within a relatively small amount of time, maybe if you ingested a gram or they intravenously put that in within basically if they put a gram in and the half-life is 14 minutes, in 14 minutes that 1 gram is now half a gram, and then in another 14 minutes the half a gram is now a quarter of a gram, and so on and so forth. So after a very relatively short amount of time, you have almost none of that radioisotope left in your system. So they can use it for testing, but like I said, if they're putting it into your body, they're going to use something that has a really low half-life, versus if you looked at, they don't want to, put carbon-14 into you because it would take over 5,000 years for half of it to decay. So that would not be a good, radioisotope to choose. So they're going to use that. And that's how they can do, like, when they look at carbon-14, that's how they do carbon dating. So if they find a piece of fabric or they find plant material and they say, oh, this is X amount of years old, they're using that, looking at how much carbon-14 still is contained in that sample compared to a living creature now. So that's how they can age things with carbon-14. All right, so here, this kind of shows you the different elements that are, in the human body. So we can remember our four main, our four main elements, that's hydrogen, oxygen, carbon, and nitrogen, making up 96.2% of our bodies. Then we have mineral elements that are 0.7% of the total body. Have major elements, 99.3 total atoms in the body. Oh, I guess they're doing total atoms. So mineral elements are going to be things that you need: calcium, phosphorus, potassium, sulfur, sodium, chlorine, magnesium. A lot of these, as we, some of them we may have mentioned a little bit in anatomy, but we're going to talk about, things about how important potassium and chlorine and sodium are as far as when we're looking at, nerve conduction and muscle contraction. Calcium is really important in muscle contraction, making up bones, things like that. But you have the mineral elements, and then you have 13 trace elements. So these are other atoms that are important in the body. So iron, iodine, copper, zinc, manganese, cobalt, chromium, selenium, molybdenum, fluorine, tin, silicon, and vanadium. Like I said, a lot of times if you look at a vitamin, like if you take a multivitamin, you'll see a lot of these in, basically in small amounts in your vitamins like that. So you'll see those. So those are going to be the elements we see within the human body. When we start looking at molecules, we're gonna be taking atoms and combining them together to form what's called a molecule, and they get held together by different chemical bonds. So we're gonna look at the difference between covalent bonds and ionic bonds that make up molecules, and we'll also look at hydrogen bonding, which is bonding between molecules that are already formed. And that's really important when we start looking at all the special properties of water. So a molecule is two or more atoms that are held together by a chemical bond. In this little diagram here, we're seeing an oxygen with two hydrogens, so H2O, that would be water. So this is representing water, and water is held together by a covalent bond. We're going to see things like sodium chloride, like table salt, NaCl, that's held together by ionic bonds. So it's an ionic bond and a covalent bond are a little bit different when we look at those. So we're going to look at these. So we have covalent bonds, which you could more specifically call non-polar covalent bonds, because there's basically two categories. Covalent, you can have polar covalent or non-polar covalent bonds. You can have hydrogen bonds, and then we can have ionic bonds. So those are going to be the different kinds of bonds that we are going to look at. So when we look at these, whether you're looking at an ionic bond or a covalent bond, or even a hydrogen bond, it all has to do with energy relationships between the electrons of atoms that are in close proximity of each other. So here, this right here is showing sodium and chlorine. So this would, when these come together, here we can see that the sodium is transferring an electron to the chlorine, and through that transfer of that electron, we're going to form ions, which are charged particles, and we're going to form an ionic bond there. So when we start looking at atoms, we kind of want to look at where those electrons are being placed. So I want to kind of remind everyone that when we are looking at these atoms, I just want to look at this and make sure that okay. I was going to draw examples and I wanted to make sure that I didn't have examples in my PowerPoint. So when we look at this, you'd want to look at your atomic number, which is the number of protons, because it's going to tell you how many electrons there are. So when we look at these, here we can see we have a hydrogen. So we have a hydrogen here, a nitrogen, an oxygen, and a carbon. So those are those four main elements found in the human body. And when we look at them, the atomic number of hydrogen is 1, the atomic number of carbon is 6, oxygen is 8, nitrogen is 7. When we look at those, we can determine where the electrons go based on the fact that the first energy shell or orbital can always hold up to 2 electrons. So this first energy shell can hold up to 2 electrons and no more. So here we can kind of see when we look at nitrogen, when we look at carbon, when we look at oxygen, we only have 2 electrons in that first energy shell. So our first energy shell can only hold 2 electrons. So write this down and then show you guys in just a second. You can only have 2 electrons in that first energy shell. In the second energy shell and above, so third, fourth, fifth, you can have up to 8 electrons. Want to write it and then I'll show you because I will write much faster. I don't have to write beside it. I really hated it. It goes to me instead of to this. All right. So we went here. First energy shell has up to 2 electrons, and then the second energy shell has up to 8. And then that's true of like third, fourth, fifth. So if we were looking at, like I said, when we have, hydrogen in its, in its nucleus, it has, the one proton, so 1 positive proton here, and then its first energy shell, it's going to have 1 negative electron. So we can kind of see that that's what's going on there. If you looked at something like carbon, so here we have carbon, it has protons, it has 6 of them. So 6 positive protons. It's kind of sloppy, sorry about that. So that means it has 6 electrons. Let me erase that. So let's read it. 6 positive protons there. This is why I don't write sideways. It's not as pretty. All right. So then in our first shell, we can have up to 2 electrons. So we have 6 electrons to work with. So we would have 1, 2 electrons here. So we have 2 electrons, but we have 6. So then our next orbital can hold up to 8, but we only have 4 left because we had 6 and we already used 2. So we would end up having 4 electrons here. So here, now we've accounted for all 6 electrons there. So you just keep on, and if you had something that was much bigger and you filled the 8, like, so let's say that when, if you did sodium, so if you went back and you're like, oh, I don't know what sodium is. So let's say you didn't know what sodium was, you could go here and look at sodium. So sodium is over here, sodium is 11. We could go there. So if we were doing sodium, I'm just gonna turn this really quick. Na has 11 positive protons in its nucleus. First shell, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This shell can only hold 8. I know I have 11 protons, so that's 11 electrons. So in its outermost shell, our sodium here would have 11 electrons because we had 11 protons. So we have to have 11 electrons. We can have 2 in that first shell, up to 8 in any shell after that. So once you get the 8 there, anything left, you'd have to do more shells. So we can kind of see that when we're looking at our little dot diagram that we're drawing for our electrons there. So it can hold up to 8. So hopefully that kind of makes sense. So when we look at those. Here. So when you look back to these pictures now, these nice little pictures, they're showing you, they didn't indicate how many protons, but 6 protons, and that's why we are, sorry, this is oxygen, so not 6. Carbon has 6, this one has 8. 8 protons, so you have 8 electrons here, 6 protons, 6 electrons, 7, 1, 2, 3, 4, 5, 6, 7. So you can kind of understand where and how they're getting these little dot diagrams. Knowing where the electrons are is going to have an impact on both covalent and ionic bonding and how these different atoms come together to form molecules. So if we look at a covalent bond, it's the strongest of our bonds. There are basically 2 types of covalent bonds. We have nonpolar covalent bonds, and then we have polar covalent bonds. So nonpolar, when you see non, that means no, and polar means poles. So when you think about like a magnet, you guys all can envision a magnet. A magnet has a positive and a negative. So if you have like 2 magnets and you try to put the positives together, they like repel each other. You try to push them together and like they don't want to go together. But if you had a positive in here and a negative in here, then they're attracted to each other. And that's why the 2 magnets will stick together. I don't know if you guys ever played with magnets when you were kids, but that's kind of the premise of that. So nonpolar means you have no pole, you create no positive or negative regions. And the way that you can create no positive or negative regions is to share electrons equally. So if everybody shares really nicely, you don't create positive and negative regions, so you'd have a nonpolar covalent bond. So for instance, if you have something like carbon dioxide, you have 2 of the same things on each side of your carbon there, and we don't, and when we look at the electronegativity values, they're relatively close to each other, so they share nicely. The oxygen and the carbon, the electrons that they share are really in between those 2 atoms equally, so you don't create any positive or negative regions. So they share nicely. It'd be like a, the carbon and oxygen are of equal strength, so the electrons they're sharing, they, you know, kind of think of tug of war. If you have two people that are equally matched and you're trying to do tug of war, who's winning? Neither one, because they can both pull with the same amount of force. So the same thing happens here. If these are both about the same electronegativity, they're going to pull on those electrons about equally, so they're going to share them, equal sharing of the electrons. Hopefully that makes sense. If you have unequal sharing, that's going to create what's called a polar covalent compound. Sorry, I'm trying to look at the time, make sure I don't go over. So polar covalent bonding is when you have unequal sharing. So one good example of this would be water. So when you see water here, oxygen is very electronegative compared to hydrogen. So when oxygen and hydrogen come in close proximity, they're going to overlap their orbitals and they're going to share some electrons. But when they share, they don't share nicely. Oxygen is much stronger, so the electron that hydrogen is bringing to this covalent bond, most of the time it's with the oxygen. So basically the oxygen is going to pull the electron from hydrogen towards itself, and it's going to create kind of a negative pull around the oxygen. And the poor little hydrogen that only had one electron to begin with, in this unequal sharing that it has, it basically is going to become positively charged. So this creates negative and positive regions in your molecule. So that's called a polar covalent bond. Try to tell people it's kind of like, think about if you had an 8-year-old and two 2-year-olds, and you're looking at like strength of, you know, if you have something that they're sharing, who is going to have that object more often? Well, the 8-year-old's bigger, the 8-year-old's stronger. If they're sharing, like, let's say a ball, 8-year-old takes the ball. Oh, I have it, it's mine now. And the 2-year-olds are like, well, they're little, they can't get the ball. If the 8-year-old's holding it up above their head, you know, and then 2-year-olds cry. So they're like, yes, you can have it. So they give the ball to the 2-year-olds for a little bit, but then when they want it back, they can just steal it. So it's kind of like, if you think about it in terms of people, it's kind of like that. It's not, the atoms don't have feelings. The atoms don't, you know, play games and do things like that. So it's not exactly like that, but sometimes for perspective, oxygen's kind of like the big kid, hydrogens are like little kids. The big kid can have the thing more often. So the oxygen is more electronegative, it's strong, it pulls those electrons towards itself, creating a negative region around that oxygen, and positive around the hydrogen that now lacks its electron. So that creates what's called dipoles, negative and positive regions. And this is going to be really important when we start looking at hydrogen bonding. Creation of these dipoles is going to allow for interactions of water molecules. So those, when we look back at these ones physically were sharing electrons. So that, like, when we were looking back at, go back, show real quick just so we can go back. Oh, no. When it does that, I just want to go with this, not back to me. Nobody wants to see me. You guys want to see this. All right, so when we're looking at this right here is showing basically covalent bonding. Here we can see that all the green dots here represent the electrons that belong to hydrogen or belong to carbon, and then the red dots are the ones that belong to hydrogen. So here, to satisfy their orbitals, because remember, when you're looking at this, a full shell in the first orbital is 2, and a full shell in that second, third, fourth orbital is 8. So the most stable form is to fill your shell. So if you were something like carbon that only had 4 in its outer shell there, it wants to have 8. So that means it can bond with up to 4 things. And basically, when it bonds with these 4 hydrogens, it's sharing the electron. So these electrons that you're seeing right here, these are sharing. So here, your hydrogen is satisfied because now it has 2 in its outer electron shell, which only holds 2. And then carbon, by sharing a hydrogen with 4, you know, these electrons from 4 different hydrogens, now when you count the amount of electrons in this outer shell here, 1, 2, 3, 4, 5, 6, 7, 8, it has a full shell, so it is happy. Like I said, happy is relative. It's not, they don't have feelings, but that has a full shell of 8 there. So it can bond with up to 4 things. But these guys are physically sharing electrons. They're overlapping their orbitals. So you can see their orbitals overlap. They're physically sharing. So no matter if you're talking about a polar covalent or a non-polar covalent bond, when you hear the word covalent, that means that they share electrons, whether it's equally or unequally, but they're sharing electrons or overlapping those orbitals. They're not transferring any electrons, they are sharing. So it's kind of like, you know, they're overlapping and sharing there. So that's a little bit different than when we talk about an ionic bond. Where are we at? All right, right here. So ionic bonds. There we go. All right, so we will see that. So when we look at ionic bonds are formed when ions are formed. So ions form when electrons are transferred from one atom to another. So here we can see sodium and chlorine, and if you remember back to chemistry, ionic bonds form between a metal and a non-metal. So if you go back to a lot of that, there's some other things that help define them that we don't typically get as much involved in the biological sense. But sodium, if we went back and looked at our periodic table, it has an atomic number of 11, which is telling us that it has 11 protons, which means it has 11 electrons. If we drew that, first energy shell has 2, second one has 8, so that's a total of 10, and then in our outermost shell we have 1. Remember, everybody wants to get that full octet of 8. They want to have 8 in their outermost energy shell. So, you know, when we look at sodium here, it's got a long way to go. It needs to get 7 more electrons to fill that outer shell. That seems kind of rough to do, try to get 7 more things. If we look at chlorine, so if you were looking at chlorine and you looked at chlorine, its atomic number is 17. So we had 2 in that first shell, 8 here, and then 7 here for our 17. So chlorine is missing 1 electron to achieve that octet, to get a full 8 in its outer shell. So if you're looking at sodium and you're looking at chlorine really wants 1 more electron to be satisfied, to be happy. Sodium would love, and I say in quotes love because they don't have feelings, would love to get rid of that outermost electron so it can drop down to a full 8 here. So if sodium and chlorine come close enough, in close proximity to each other, sodium is more than happy to get rid of or transfer its electron to chlorine. And so then sodium has a full 8 in its outer shell because it got rid of this one here. So this is no longer here. So it has a full 8 in its outermost shell now. Chlorine needed 1. It got that 1 from the sodium. So now it has a full 8 in its outer shell. So everybody's happy. Everybody's great. However, because they're close enough to transfer those electrons, when they transfer the electrons, they become what's called an ion. So an ion is a charged particle in which the protons and electrons no longer equal each other. So here, when this goes, when we look at this, I'm gonna draw sodium and a chlorine for you guys real quick. And so remember, we have 11 protons in nucleus, and I'll show you guys this in just 1 second. Stand by. Chlorine. Chlorine's a pain because it has so many. All right, so with this. Ooh, why is that so red? Let's see. Okay, that made it better. Still a little pink. I don't know why it's pink. My paper's white. All right, so we look here. Sodium has 11 protons, 11 electrons. Chlorine, 17 protons, 17 electrons. If these come close enough proximity, this electron over here is going to get transferred over here to chlorine. So this is not here anymore. So if we went through now and looked at this, we still have 11 positive protons, but now if we counted up our electrons, we have negative 10 electrons. So overall, we have a +1 charge. So Na is a +1. Over here, chlorine has positive 17 protons. And now, because it gained this electron here, it has negative 18 electrons. So overall, it has a -1 charge. So chlorine is a minus. So when we look at that, we can kind of see, okay, that does look okay. So we can see the number of protons doesn't change when it transfers that electron, but when it transfers an electron, whether it's giving away or receiving, that changes the number of electrons. And so the protons and electrons no longer equal each other. So then you have these charged particles. So this is called, when you have a charged particle, this is an ion. So ion, these are both ions here. This is a positive ion or a cation. This is a negative ion or an ion here. But no matter what, when they transfer that electron, if they're close enough to transfer an electron, once they've transferred the electron and become charged particles, they are then attracted to each other like magnets and will come together and form an ionic compound. So Na, this is why I don't write sideways, very bad, NaCl, and this formed from an ionic bond because you transferred electrons, formed ions or charged particles, and then because of the attraction of the opposite charge, they come together, and that's what forms that ionic bond. So that's different because remember our covalent bonds, they were physically overlapping their orbitals and sharing. So with the ionic bonds, they transfer electrons, they become then charged particles, which are ions, and then those ions are attracted to each other, and that's forming ionic bonds. So an ion is an atom that gains or loses electrons. An anion is going to be the electron acceptor, so it's going to have more electrons than protons, so it's going to be negatively charged. The anions are negatively charged. Cations are the electron donor, so they're giving away electrons or losing electrons, however you want to think of that, and they're considered a cation. I always think about cat has a plus in it, so these are the ones that become positively charged. So to become positively charged, you had to lose electrons. I think that Dr. Calkins says cations are positive, like pause like a cat. So, you know, I won't credit that to myself. It's not my pun. So cations are positive because of the loss of electrons, because your proton number doesn't change. All right, so this is showing you what I showed you there. So NaCl is formed from ionic bonding. One atom has one electron in its outer shell, that's your sodium. Your chlorine has 7 negative electrons, so it transfers, sodium will transfer to the chlorine. They become a sodium ion and a chlorine ion, charged particles that are attracted to each other, forming that ionic bond. When we look at the attraction, like if you put something into solution, so here we have sodium chloride, so these are all held together by basically like magnets, attraction of opposite charges. Water is held together by that polar covalent bonding, so the oxygen and hydrogen physically overlap their orbitals, and that's what's holding that water molecule together. But remember, water is polar covalent, they're not sharing nicely, and it creates those positive and negative charges, regions, those dipoles. So when you put salt into water, why does it dissolve? Well, the attraction between these positive and negative dipoles will kind of rip apart those sodium and chlorine, and they will surround them, and so that then it goes into solution. Excuse me. All right, so how much more? we have? All right, a little bit. All right, so this is called ionization when those atoms become ions. You get a lot of groups that will ionize, so like carboxyl groups, amino groups, and we're going to see some of these things like amino groups when we talk about proteins. They can ionize. I'm going to stop here with this part of the presentation, and I'm going to do a second, much shorter video for the last part of this chapter, because I have to go to a meeting in a few minutes. So I will pick that up, and we will review ionization real quick, and then finish the last little bit of this chemistry review so you have that information available to you.